So, a detailed study of kinematics of spatial chains, especially robots, you would find in any robotics course, typically uses a matrix method, but we will just look at some of the basics of this method applied to spatial mechanisms. So, the basic idea is you will have a Cartesian coordinate system attached to every link. And usually you follow certain conventions. One of the most common conventions for defining these systems is the Dennewitt-Hartenberg method, which is the book that we are using for this course. Those two authors are very famous in the robotics literature for this, the Dennewitt-Hartenberg coordinate system method for assigning coordinate systems. So, once these are defined in this manner, the two coordinate systems are related, or the coordinates of a point in space expressed in two such systems are related through a 4x4 matrix, which is called the homogeneous transformation matrix. So, we will see how that is done. And then once you do this, the loop closure equation is expressed in matrix form. Okay, through these transformation matrices. So, first let us look at two coordinate systems actually I will just go. Two Cartesian coordinate systems that are rotated with respect to one another, but share a common origin. Okay. Two coordinate systems. So, let us say there is a point P located in space and we want to express this point P. So, it has a certain set of coordinates in the x naught, y naught, z naught coordinate system and another set of coordinates in the x1, y1, z1 coordinate system, and we want to relate the two sets of coordinates. So, let us say point P is expressed or located by vector P naught. Let us say the x naught, y naught, z naught coordinate system is the absolute or fixed coordinate system. So, it is probably the coordinate system attached to the fixed link of the mechanism. In the absolute coordinate system, O x naught, y naught, z naught, and by P1 in the rotated coordinate system O x1 y1 z. Okay. So, both are descriptions of the same point position. So, if it is described as say in P0 I have P naught x along the unit vector x naught plus P naught y along the unit vector y naught plus P naught z along the unit vector. So, the caps denote the unit vectors. Okay. So, this is the same as, because they describe the same point, P x1 along unit vector along x1 plus P1 the z component along the z1 direction, because both are descriptions of the same point. Okay. So, now I will dot product both sides by x naught. So, I have, let us see, I have plus P1y along y1 cap plus P1z along z1 cap, and if I dot product both sides x naught. Okay. Now, what do I have? All these two are Cartesian coordinate systems. So, the vectors are orthogonal. So, in a particular system x naught, y naught, z naught are orthogonal to each other. So, their dot products will be 0, right, and x naught dot x naught will just be 1. So, I eliminate all the other terms on the left hand side and I will get this is equal to x1 dot x naught Pz1. Similarly, instead of with x naught, if I do the dot product on both sides with y naught, in succession if I do with y naught, then z naught will get Py0 equals Py1 plus z1 dot y naught Pz1, and this is by doing the dot product with z naught. I will get Pz naught equal to x1 dot Px1 plus y1 dot z naught Py1 plus z1 dot z naught Pz1. Okay. So, in matrix form I can write this as is equal to x1 dot x naught, x1 dot y naught, x1 dot z naught, y1 dot x naught, y1 dot y naught, y1 dot z naught, and here z1 dot x naught, z1 dot y naught, z1 dot z naught into Px1, Py1, Pz1. In a compact form, I can say that the coordinates of P in the 0 frame equal a matrix R10 times the coordinates of P in the frame 1. Okay. This matrix here is called a rotation matrix. It relates the orientation of the frame x1, y1, z1. It shows how that is rotated with respect to the frame 0, frame 1 with respect to frame 0. So, this is the notation, rotation of frame 1 with respect to 0, and if you look at the columns of this matrix, then you see that this column here gives you what? If you look at x1 dot x0, x1 dot, these are the direction cosines of x1 with respect to frame 0. These are similarly the direction cosines of y1. So, the columns of this rotation matrix are basically the direction cosines of the 3 unit vectors defining frame 1 with respect to frame 0. So, these are 9 quantities in this matrix, right. So, do you need 9 quantities to describe the orientation of one coordinate system with respect to the other? So, how many independent quantities are these? You have only 3. The axes are coincident, the origins are coincident. You only have 3 independent quantities, and that is because you already have the the x1, y1, z1 are orthogonal, you know that, right. So, that gives you three relations. In addition, you have each column, the sum of the squares, the direction cosines equal to 1. Okay. So, it is only 3 independent quantities that you have in this matrix. So, nine quantities describing the direction cosines of the axis of only 3 are independent. Equal to 1. Okay. So, you have R1 0 equal to x1 dot x naught, x1 dot y naught, x1 dot z naught, and then you have y1 dot x naught, y1 dot y naught and y1 dot z naught, z1 dot x naught, okay. So, if I want the rotation matrix, how is this? So, I want to look at it from the angle of the x naught y. So, I want to see what is the rotation of x naught y naught z naught with respect to x1 y1 z1. Okay. So, this is the inverse of this matrix, but I can, from the direction cosines, I know that it has to be x naught dot x1, x naught dot y1, because this is my reference now. So, I want the direction cosines with respect to x1 y1 z1, y naught dot y1, y naught dot z1 and z naught dot x1, z naught dot y1 and z naught dot z1. Okay, this is the inverse of this, and if I look at these two, how are they related? This is nothing but the transpose of the original rotation matrix. So, such matrices where the inverse equals the transpose, they are called orthogonal matrices. So, the rotation matrices are orthogonal matrices. Yeah, right. So, the sum of the DC is equal to 1. So, the sum of each row, each column equals sum of the squares, each row and each column equals 1. So, let us do some basic rotation matrices, just so we get familiar with. So, let us say we have and I have another coordinate system x1, y1, z1, where the rotation happens about z0, so that z0 and z1 are aligned. Okay. So, I have a rotation of theta of O x1, y1, z1 about the z0 axis. Okay. Typically we follow the right hand rule. So, if there is the positive sense if you have a positive rotation of theta is when if you have a screw, you have a right handed threaded screw, and if you move along the direction of theta, then the screw advances along the positive axis, in this case the z axis. So, positive sense of theta is given by the right hand rule. Okay. So, a positive rotation of theta advances axis. So, construct the rotation matrix for this. What are your direction cosines? You have what is x1 dot x naught? Cos theta. x1 dot y naught is the angle between x1 and y naught is 90 minus theta, which is sin theta. Okay. And dot z naught. What is the angle between z1 and z naught are parallel, which means it is coming out if this is your plane. Okay, which means x0 and z0, x1 and z0 are perpendicular. So, you have cos 90, which is 0. Similarly, y1 dot x0, what is y1 dot x0? Cos of 90 plus theta. Okay, minus sin theta. Then you have y1 dot y naught cos theta, y1 dot z naught equal to 0. z1 dot x naught is 0, z1 dot z naught is 1. Okay. So, my rotation matrix relating 1 with 2 is, so short form we will write cos theta is c subscript theta sin theta 0 minus sin theta cos theta 0 0 0 1. So, we can we designate this, since this is a special rotation, we will call this r z theta. Okay. So, these are considered the basic rotation matrices, where similarly I can write r y theta would be cos theta 0 minus sin theta 0 1 0 sin theta 0 cos theta, and I have r x theta is 1 0 0 which one? R y theta, yeah. Which term are you, you have a question about the r y theta matrix? What are you saying? Are you saying it's 1 theta? Minus sin theta here. Oh, sorry. No, this is fine, this is fine. This is, yeah, it's fine. So, this is, what is this term correspond to? You are talking about a rotation about the y axis, right? Here itself you can change this and see. Okay, I can take this as y z and x. No, I want this as y. So, this will be x y z. Change it like that. Okay, I want a rotation about the y axis. Do the direction cosines. x1 dot z naught when you are rotating about the y axis. Okay. Let us do another, I want you to try this. Let us say I have x naught okay, still a right handed system, and let us say y naught is coinciding with z1, and I have x1, this angle is 45, and I have y1. Orientation of okay. Take a few minutes to try it out. Do the direction cosines. x1 dot x naught is what? What is x1 dot x naught? 1 by root 2. x1 dot y naught. This is coming out, right? So, it is 0. Y naught is parallel to z1, which is 0. What is x1 dot z naught? Hmm? 1 by root 2, yeah. Then y1 dot x naught, y1 dot y naught, y1 dot z naught, then z1 dot z naught 0, sorry, z1 dot x naught, yeah, z1 dot y naught 1, z1 dot z naught is 0. Okay, you just apply the same direction cosines. Okay. Now let us look at if you have multiple rotations happening, how these rotations are composed. So let us say we have 3 frames, O, x2, y2, z2. So the origins are coincident. I have P naught equals R10 P1. Let us say I have P1 can be described as this, okay, with respect 1 and 2 can be related in this fashion. Then P0 is R10, R21, P2. So you can see it goes like this. Okay, you can see that, you can think of it as these terms cancelling out, right, 2 and 2, 1 and 1, cross terms cancelling out. And this I can write as R20 P2. Okay. Therefore, R20 is okay. And remember, matrix multiplication is not commutative. So this is different from, so the order of the rotation matters. Okay. So we take it as rotation occurs first with respect to frame 0, or that is the first matrix, then frame 1. Okay. So order of rotations matters. Okay. So these are the cases where you have the origins of the two coordinate systems coinciding. Okay. In a more general case, it is not going to happen. So you typically choose, say, coordinate systems attached to the CG of each link. Okay. The chances of the CGs of all the links coinciding is very low, right. So a more general case is when you have a base coordinate system and then you may have another coordinate system which is both rotated as well as translated with respect to the first coordinate system. So, let us say the origin, so O1, this is O0, is displaced by some d1. So, this d10 represents the displacement of the origin O1 in the reference frame 0, and then let us say we again have a point P which has a certain description described by this vector P1 and by a vector P0 in this. Okay. Typically, when you have two coordinate systems, if the coordinate systems are parallel, then I could say that P0 equals D10 plus P1. However, when the coordinate systems are rotated with respect to one another, you cannot directly add the two vectors. I cannot add a vector expressed in coordinate frame 0 directly to a vector that is expressed in coordinate frame 1. So, this would be expressed as P0 equal to, so suppose I had that coordinate system shifted to this origin, okay, then the description of that would be this plus D10. So, I cannot directly add P1, I have to transform everything to the same coordinate system. So, this vector transformed into a coordinate system that is parallel to x0, y0, z0 would be this term here. You multiply it by the rotation matrix, because we saw in the previous case when the origins were coincident that those two representations are equal. So, I have converted everything into this base coordinate system before I can add these vectors. Okay. Because P0 and P1 are expressed with respect to non-parallel coordinate frames. Do you remember when we did the force analysis, one of the things that I insisted on or I mentioned repeatedly is the local non-rotating coordinate system. We expressed all those position vectors for the points of application of the forces, etc. So, in each case there we took a coordinate system with the origin at the CG, but we said it remains parallel to the global coordinate system. Okay. So, that is the case where you have a non-rotating coordinate system. So, that is when you can add those vectors directly. If they were expressed in coordinate systems that are rotated with respect to one another, then you have to apply the appropriate rotation matrix in order to be able to add vectors in these two coordinate systems. Okay. So, basically multiplying P1 by R10 expresses it in a coordinate system that is parallel P0. Okay. In this case, these vectors can be added. You can do the translation first. So, this is a description of a general rigid body motion. This represents where you have a rotation and a translation. This represents a general rigid body motion, can be represented as a translation followed by a rotation, or you can do the rotation first and then do the translation. So, it does not as long as they are both with respect to the same frame, the order in which you do the translation and rotation do not matter. So, if we have two rigid motions, we have P0 equal to R10 P1 plus D1, and say we have P1 equal to R21 P2 plus D21. Then I can substitute this into this and I will get P0 equal to R10 R21 into P2 plus R10 and this I can represent as R20 P2 plus D20. Therefore, if I compare the two, I get R20 equal to R10 R21, which we saw earlier when we composed the rotations, and D20 is D10 plus R10 D21. Okay, so this represents the translation of the second coordinate frame again. So, when you are working with manipulators or spatial mechanisms, these transformations have to happen to express everything in the same coordinate frame. Okay, where so in matrix form I can write this as R10 D10 0 1 So, we say the rigid motion of the form, we call it H for homogeneous transformation matrix, and we say R0 D 1. Okay. So, this will be a 4 by 4 matrix. This is a 3 by 3, the rotation matrix. This vector is a 3 by 1. Okay. This is the matrix representation of a rigid motion. It is called the homogeneous transformation matrix. So, we saw here, so we have this P1 equal to R1 plus D10, right. So, essentially what we have done is, you have and I put a 1, a fourth column I add, and here I have the R10, which is a 3 by 3, okay, and this is D1 x, D1 y. So, the origin, right, this is a 3 by 1, and then I add 0 0 0 1 into P, sorry, this should be 0. Did I do this wrong? Yes, nobody corrected me. This is 0. And this is 1. Okay. It is basically this equation in this form. Okay. So, we call this, so we typically call this in matrix form, we will write this as P, a capital P0, we define this as P0 1, capital P1 is P1 1, okay, it becomes a 4 by 1, this is a 4 by 1. And then, so we can write this as P0, capital P0 is equal to H10 P1. Okay. Do the loop closure, let us see. So, you can use certain conventions to set up these matrices. Okay. The Denevit-Hartenberg convention is one. So, where you choose these coordinate systems. So, if you have n links in the mechanism, you choose the coordinate systems that you attach to each of these links, okay, and the coordinate systems rotate with the links, as opposed to the earlier case where we said we are choosing only the origin at the CG of the link, but the coordinate systems remain parallel to the ground coordinate system, or the fixed links coordinate system. So, here you would attach these coordinate systems to the individual links, so that they rotate with the link, and then you would relate the coordinate systems to one another through these transformation matrices. So, that takes into account the rotations of the links, because you are now expressing everything in terms of these transformation matrices, which contain the information about the relative orientations and displacements of these links with respect to one another. Therefore, now if I want for any specific point on the link, if I know the description of that point with respects to that link's own coordinate system, I can easily relate it and find its spatial location with respect to the ground coordinate system. So, that is the that's sort of the idea behind doing it in this systematic fashion. That way, any point on any link that I want, once I know the relationship between the coordinate systems, I can determine the kinematics of that. Okay. So, this seems like a good point to close this course. Okay. So, this would be the, because doing it in a geometric or using geometry or trigonometry will become very complex when you try to look at spatial mechanisms. So, this is, I hope this has given you an introduction to spatial mechanisms, but predominantly our course was about synthesis of planar mechanisms, and I hope you have gotten a good idea of that over the course of this semester.